Okay, I apologize for the technical glitch that just happened. I was lecturing, babbling away as usual, and the device wasn't recording anything. I don't really blame it, but there you go. So I want to try to pick up the lecture from where I left off. We were just looking at the situation where we had a hunk of plastic that was bathing in an electric field, and we showed how the molecules polarize and so on. Very nice conceptual question. But now let's go and do a calculation, a very simple calculation. And this calculation is, excuse me just one moment. The machine has locked me out. Excuse me for a second. Okay, so this is problem number 43 in chapter 19, and the question reads, what is the magnitude of the electric field produced by a charge of magnitude 7.5 microcoulombs at a distance of 1 meter and at a distance of 2 meters? Okay, very, very simple problem, but it's always good to start simple, and that's what we're going to do. Okay, so this is problem number, this is chapter 19, problem number 43. And so it tells us that we have a charge here of Q equals 7.5 microcoulombs. There's our charge, and as you know now, that charge will create an electric field everywhere in space. And so let's go and try to calculate that field somewhere in space, namely a distance 1 meter away from the charge that's creating the field. Now, one thing I want to point out here is we're calculating the electric field here. There is no charge here to feel the effects of the field. Doesn't matter. This guy is creating the field everywhere, and we can calculate the field some distance, any distance, from the charge, whether we have a charge here or not, whether we have a charge in this location or not, okay? So we go back and we say, okay, what's the electric field due to a point charge? That's the only electric field we know just yet. We don't know the electric field due to a hunk of metal that's charged up or anything else. The only electric field we know thus far is the electric field due to a point charge. And the magnitude of that field is given this way. KQ over R squared, where R is the distance between the charge and the point at which you're calculating the electric field. From the charge to wherever you're calculating the field. That's the distance R that appears in this formula. Q, of course, is the charge that's creating the field in the first place, and K is our Coulomb constant that we've learned earlier. Okay, so let's plug the numbers in. K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Q is 7.5 microcoulombs. Now, question, can I just throw the 7.5 in here and everything will be merry? No, right? Because we've already chosen our units. By putting the constant down as this, we've chosen our units to be in coulombs and meters. So we've got to use coulombs and meters in the rest of the calculation. So we've got to convert the 7.5 microcoulombs to coulombs. So it's 7.5 times 10 to the minus 6 coulombs. And we're going to divide by the distance squared, the distance from the charge to the point where you're calculating the field. And that is 1 meter quantity squared. Okay, and our electric field comes out to be 6.74 times 10 to the 4th newtons per coulomb. So very simple calculation, but it does a couple of things for us. Number one, we get back to the units of the electric field, newtons per coulomb. Let's look at it. This coulomb will cancel one of these coulombs. This square meters will cancel the square meters up here, and I'll end up with newtons per coulomb. Okay, and that's what I wrote down here. Okay, now, that's part A of the problem. In part B, they say, Okay, what happens? Go and calculate the electric field, not at a distance of 1 meter from the charge, but at a distance of 2 meters from the charge. All right? And so that's going to be, once again, KQ over R squared. But R squared in this case is going to be 2 meters. Okay? And when we pop all the numbers in, this comes out to be 1.69 times 10 to the fourth newtons per coulomb. Okay? Notice one thing, just as I talked about earlier, that we have now doubled the distance. Here is the second one. Here's another 1 meters. So in this case, the R value is 2 meters, and so we expect the electric field to go down by a factor of 4, because we've doubled R, and R is squared, so E should go down by a factor of 4, and that's exactly what happened here. Okay, because 6.74 is 4 times greater than 6.9 or 6.85. Okay? All right, let's move on to a slightly more difficult problem. And I'm just going to spritz the board a little bit so we get a nice clean slate here. Okay, in this problem is problem number 80 in your textbook. Problem 80 from chapter 19. And let me just bring that up on my screen so that I can read it. Okay, and this problem number 80 in chapter 19 says, a point charge at the origin of a coordinate system produces the electric field E equals 36,000 newtons per coulomb x hat on the x-axis at the location x equals minus 0.75 meters. Determine the sign and magnitude of the charge. All right. Now, it's hard to just sit and listen to a problem like that when you can't see it, so I'm hoping you're looking at your textbook right now, but if not, I'm going to set it up for you. So what it says is that we've got some mysterious charge here. We'll call its charge Q, and it's sitting at the origin of the coordinate system. The only other thing we don't know what the charge is, but we do know that if we come over here, a distance of minus 0.75 meters in the negative x direction, we know what the electric field is at that location, and they give it to us. They say the electric field is 36,000 newtons per coulomb x hat. So it's a big field, sort of, 36,000 newtons per coulomb. The key thing here is that its direction is in the plus x direction. So let's draw that. There's the electric field vector at that location. And here it is. The electric field is 36,000 newtons per coulomb x hat. So it's in the plus x direction. Now, the question asks, find the sign and the magnitude of the charge. All right? How do we find the sign? Let me let you think about that for just a second. How do we find the sign of the charge? Okay? The sign is found from looking at the direction of the electric field. Remember that a negatively charged particle has field lines that are pointing inward toward the charge. Like this. Okay? Electric field lines point into a negative charge. What's happening with this electric field? Look at it. At that location, it's pointing inward toward the charge. Ergo, that must be a negatively charged particle. So Q is a negatively charged particle. Okay? So that's the first part of the problem, the sign of the charge. Now let's take a look at the magnitude of the charge. How are we going to get that? Hey, we know what the magnitude of a point charge, we know what the magnitude of the electric field due to a point charge is. It's kq over r squared. Okay, so let's look at it. K is 8.9, excuse me. We don't know what the charge is. We're trying to find the charge. So let's solve the equation for Q. So Q equals r squared E over K. We know what R is. This particle is sitting 0.73 of a meter away from the charge. So that's going to be 0.75 meters quantity squared times the value of the electric field, magnitude, 36,000 newtons per coulomb. And we're going to divide it by our Coulomb constant K, which we know to be 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. All right, and the magnitude of the charge, when we plug that into the calculator, it comes out to be, let me just get my notes, comes out to be 2.25 times 10 to the minus 6th coulombs. So, what we know is then the charge is minus 2.25 microcoulombs. There it is. We found the magnitude just by applying the electric field formula for a point charge. Remember again, it's only good for a point charge, for nothing else. But that's what we have here. We have a point charge. So here it is. We calculate Q magnitude. We know that Q is negatively charged because the electric field vector for a negatively charged particle will point toward the charge everywhere. We only have one electric field specified in the problem, but it is pointing inward toward the charge, so we know it's negatively charged. So this is the final result. Okay? All right. Thanks for listening. I will be back on Monday, and we'll continue the discussion then. Thanks very much for your attention.